Hi, this is Kevin Iga again with Math 141 Lectures, lecture number 3. So we've been covering Gaussian elimination. We've been doing that in section 2.1 of the book, and we're going to finish up 2.1, talk about 2.2, and let's just review where we've been. So we've been solving systems of linear equations using this method called row reduction or Gaussian elimination. And there are these three kinds of operations. Okay? Swap two rows, multiply a row by a number, but not zero, add a multiple of one row to another. Okay? Those are the three kinds of operations. They don't change the set of solutions. So whatever was the set of solutions before, the one you want, is the set of solutions for the resulting matrix when we do these operations. And the idea is if I do these operations in the right order and do the right ones, then I'll end up with something that is much easier to understand. Whenever we want to get a 0, we use an operation of type 3. Whenever we want to get a 1, we're going to use an operation of type 2. Sometimes operations of type 1, as you saw last time, would be involved in the process of getting here. And the idea is we start in the upper left. Okay? The goal is to turn this into a 1. Okay? And depending on what's here, will determine how we do that. If it is not 0, for instance, if this is a 5, I'm going to multiply this whole thing by 1/5. Okay, that's what this says. I'm going to multiply this row to make it a 1. The only time this fails is if this is a 0. But let's say it succeeded in this case. Let's say this was a 5. I multiplied through with 1/5, and I succeeded in getting a 1. I'm going to use it to clear the rest of its column to 0 using operations of type 3. Okay, and all of these will now be zeros. Then I'm done with this box, and I move down to the right, and I work on this one. And again, I try to make this one a 1. If it's 0, then I have to swap with a lower entry to make it a 1. Okay, we're swapping not only the entry, of course, we're swapping the entire row, but I'm just focused on which row I take is going to be dependent on which one of these things is not 0. Okay, and let's say I succeed at that. As soon as I get that to be something non-zero, then I go through here again and multiply this to make it a 1. As soon as I get a 1 here, I use it to clear everything else into 0. As I said, these are called pivots. I go down here, try to make this one a 1. And if this is a 0 and everything under it is also 0, okay, then these can't be done, and I have to just abandon this and move to the right. That's what this says. Move to the right. And I try again, try to make this a 1. Maybe this succeeds. I use it to clear it to 0. Go down to the right. Let's say this one, there's a 0 and everything underneath it is 0. Again, you abandon it, move to the right, and so on until we're done. Notice, by the way, that you might have some columns that you don't reach. Yeah, that's fine. All right, so this is what's called Gaussian elimination. After I've done all of these steps, if I do it in this way, what I end up with is a matrix that has these ones in the boxes, these pivots, and there might be other ones as well, but I'm focused on these ones because these are the ones for each row. It's got the first one that's there, and in its column, everything else is 0. And everything underneath this sort of staircase here is 0 as well. Okay, so this is called reduced row echelon form. Okay, sort of those of you who know French know échelle refers to this kind of staircase shape here, and this is what is the result of doing Gaussian elimination correctly. This is the final stage. This is the final form of your matrix. A special case of that, of course, is the ones go down the diagonal. That's also that's the initial example that I had for you before. This is a slightly more general situation when that's not possible. Every matrix can be put into this form. There might be some computer programs out there, and as well as things online, things on your calculator that will refer to reduced row echelon form. So there are programs out there that will do this entire procedure. By the way, if you haven't done the homework for today, or that was due previous to this lecture, go ahead and do those. But don't use those programs to do those homework problems. But from here on out, you can use the homework that I'm assigning today. You can go ahead and use whatever program you want. The idea is this. it's important that you have some practice doing actual steps, doing actually these row operations, and the only way to really know it is to do it. If you don't try doing that, then if the first time you have to do that is on the exam, oh, that's going to be terrible. So make sure you practice that. Um, from here on out, though, I think you'll have enough practice that you can keep on just using whatever program you want, because now the focus is not going to be on how to get here, but what do we do with this as a result. Okay. So here's an example. I'm going to give you a whole bunch of examples, and some of these will showcase some interesting features that you might not have seen before. So here's one example. Okay. X plus 2y equals 4, 2x plus 4y equals 13. Okay. So you just dutifully copy the coefficients into this matrix, 1, 2, 4, 2, 4, 13. This is a 1, okay, it's already there. I have to make this a 0, so I multiply this by -2, add it to this one, and I get this row here. Okay. Now I've cleared the rest of the column to 0. Now I'm here trying to turn this one into a 1. It's a 0. I look under it, and there are no rows under it. So there's no possibility of swapping. And I move to the right, and I hit the edge, the equal sign here. So this is done. Okay. What happened here? Well, if you think this says x equals 4, y equals 5, be careful. Okay, that's not what this means. Okay, don't just read these numbers off as your answers. You have to read these as equations. Okay, this row says 1x plus 2y equals 4. This says 0x plus 0y is equal to 5. In other words, x plus 2y equals 4. That's the first one. The last one says 0 is equal to 5. That's a very strange thing to say, isn't it? I mean, 0 is equal to 5? Come on, 0 is not equal to 5. Actually, that's the point. 0 is not equal to 5. The set of x's and y's that satisfy this equation are the same set of x's and y's that satisfy this equation, or this system of equations. And in particular, both of these have to be true. And depending on what x and y is, maybe this first equation might be true, but the second equation is certainly not going to be true, no matter what I choose for x and y. And so, there are no solutions. Therefore, from this, there are no solutions here. Because remember, these operations don't change the set of solutions. So as soon as I see this 0 equals 5, the way I see this is there'll be zeros over here, and then something that's not 0 over here. I know there are no solutions. Let's try another example. Here's x plus y equals 6, 2x plus y equals 1, x plus 2y equals 10. Got this matrix here. This is already a 1, and use this to make these zeros and add multiples of this row to this row, and you get something like this. If I read off the equations, this says x equals -5. This row says y is equal to 11. This row says 0 equals -7. Now be careful. Don't jump to the conclusion that x equals -5, y is equal to 11. That's not so. Once you have the 0 equals -7, I know there are no solutions. Okay? So there's no solutions to this either. By the way, what's really happening here is somehow some of these equations contradict the other ones. This doesn't tell us which ones contradict which ones, but rest assured, these equations contradict each other. Okay. It's easier to see actually in this one. X plus 2y equals 4. If I multiply this by 2, I get 2x plus 4y equals 8. So 2x plus 4y equals 13 is incompatible with this one here. It contradicts it. Here it's a little bit harder to see what the problem is, but that is still no solution. There's some kind of combination of these equations that is impossible. This is, by the way, what tends to happen when you have more equations than variables. It doesn't always happen, actually, but let me show you an example where it doesn't happen. So let me use this, but just change one of these numbers. Okay, I changed this to 17 here. And let's look at what happens. Here's the matrix, and I do all these operations. I'm skipping, showing you all the steps here. But you've got this one a 1, this one a 1. And this one is a 0. As opposed to here that was -7. Here it's 0. So this says x equals -5, y equals 11, 0 equals 0. Okay, 0 equals 0, that's not a contradiction. It's just true. So what does that mean? That means that, well, x can be -5, y can be 11, and 0 can be 0. I don't have to say 0 equals 0 because all I'm asking for is the solution. The solution says x equals -5, y equals 11. Okay. What this means, by the way, is that one of these equations is redundant. It's maybe a little bit hard to see where the redundancy lies, but that's what this tells us. Whenever I see this 0 equals 0, that means one of these equations could have been dispensed with, and it's implied by the other ones. All right, here's another example. Okay, I'm going to actually show you one where we swap rows. So here we try to make this one a 1. It already is 1. Try to make this a 0. Okay, so I multiply this by -2, add it to that one. Okay, and now move down to the right and we get this. And here we have a 0. And I'm going to use this one. Well, I want to make this a 1. It's a 0, so I look underneath it, and here we go. Here's a row that's not 0. So I'm going to swap rows 2 and 3. Okay. Notice, by the way, 0, 0, 1, 2 became down here 0, 0, 1, 2, and 0, 5, 6, 1 became here 0, 5, 6, 1. I swapped the entire row. I didn't just swap these two numbers. Okay. I look at these to figure out which row I'm swapping with, but then once I decide on that, I swap the entire row. Okay. And now this is a 5. I can use that to multiply this by 1/5 to make this a 1. Use it to clear this to be a 0. This is going to be a 1. This is actually going to work out to be a nice one. There's not going to be any contradictory rows or anything like that. Okay, you can keep on going with that, but I've shown you this example. Let's go to another example. All right, here it's kind of similar. I'm going to take this one, multiply it by -2, add it to this one to make this a 0. Okay, and it turns out like this. And I'll try to make this a 0. Sorry, try to make this a 1, and it's a 0. I look underneath it, and there's a 0. That means I have to skip this and go here, and make this one a 1. And so sometimes you need to do that, okay? And there's several different things that could happen here. But in this case, you get this row of zeros here. That means something's redundant. Okay. And here's the matrix again. If you write these out as equations, you see x plus 2y is equal to 1, and z is equal to 2, and 0 equals 0. You can ignore the 0 equals 0. That doesn't do anything. And we've got these two equations. Now, this does not look like a solution, right? I mean, a solution, z is equal to 2, that's nice. But what is x? What is y? Okay, so here's what we're going to do. We're going to solve this for x. And then, so x equals 1 minus 2y. And then y is anything. And then z is 2. You might not have seen this sort of thing before. You probably have not seen this sort of thing before. So let me tell you what this means. Pick any value. Any value? Yeah, any value. Any number for y. And then this equation says I plug this into this equation here, and that'll tell me what x is. And then z is 2 no matter what. For example, okay, so this was the original set of equations, right? The original set of equations way back here. And this is what we wrote as our solution. So I'm going to pick y is equal to 3. I know that's not in the order that this is written, right? I'm picking this one because it's any value. Y is equal to 3. Plug that in here. Okay. And then x is 1 minus 2 times 3. 1 minus 6 is -5. So here, x equals -5, y equals 3, z is equal to 2 is a solution to this. Okay. It makes this equation true, it makes this equation true, it makes this equation true. And just try it, right? I'm not going to do it right now. You can plug in -5 plus 2 times 3 plus 2, see what you get. And plug it into here, here, and here as well. See if you get 8. And of course, z equals 2. That's obviously going to be fine. But you didn't have to plug in 3. You could plug in any other number. You could plug in 0. Okay, plug in 0 into here. And then plug 0 into this equation here. 1 minus 0 is 1. And z is equal to 2. So plug these into here. X equals 1, y equals 0, z is equal to 2. 1, 0, 2. 1 plus 2 times 0 plus 2, that's 3. 2 times 1 plus 4 times 0 plus 3 times 2 should be 8. Just check, and z is equal to 2. So here's what we do. This is how we write our answer. Okay. There are infinitely many solutions to this, one for every value of y. And so you can't possibly write them all down. So by writing this, I'm giving you a prescription for how to find the answers. And so you just plug in any number for y, and then plug it in here and here, and then you're going to get a solution. And you can try different numbers, see what kind of solutions you're going to get. There are infinitely many solutions here. So this is how we write it. Okay, we can't possibly list them all. We just write this down, and this tells us how to get all the solutions. So here's what we're going to do. Once we get it into reduced row echelon form, we're going to write each row as an equation. Then the ones that are the pivot ones, the ones that put in those squares, there might be other ones around in the matrix. Those don't matter, but the pivot ones, are going to solve each row for these. And the other columns are going to be free to be any value. So here's an example. Now there's so many columns. I mean, obviously I need more letters of the alphabet. So I'm going to call the variables A, B, C, D, E, F. Those correspond to the columns, right? A, B, C, D, E, F. And then you notice this is in reduced row echelon form. This is the 1, this is a 1, this is a 1, and then everything in its column is 0. Okay. And the first step is write each row as an equation. A plus 3b plus 2d plus 4f is equal to 10. Okay. The second equation is c plus 5d plus 2f is equal to 3. Remember, these are called A, B, C, D, E, F for each of the columns. The last one says e plus 7f is equal to 2. Then we're going to look at the pivot ones. That's this one, this one, this one. You can tell because these are the first variables in each of these equations, and we're going to solve for these. That means all of these other ones are going to put to the other side of the equation. All the other ones are going to be free to be any value. So that's what? B, D, F in this case, the ones where there's no pivots. And it looks like this. A is this. Just move these to the other side of the equation. 10 minus 3b minus 2d minus 4f. B can be any value. C is going to be, again, solve for C. Put these 5d and 2f to the other side. C is equal to 3 minus 5d minus 2f. D can be any value. E is going to be 2 minus 7f. F can be any value. So in this case, because A, C, and E have the pivots, okay, those are the ones that are going to have these equations, A, C, and E. And because B, D, and F were the ones without the pivots, those are the ones I'm just going to say any value. And so B can be anything, D can be anything, F can be anything. They're not going to necessarily even the same thing. I mean, B could be 5, D can be 10, F could be 34. And then you just plug it into these things, and you're going to get values for A, C, and E. And that will be a solution. Again, because any number could work for these, there are infinitely many solutions to this problem. All right, so the summary here is there are 3 options. Either a system of linear equations has 0, 1, or infinitely many solutions. A linear system will not have 2 solutions. I mean, a quadratic might, but this is a linear system of equations. Two solutions is not a possibility. It's either 0, 1, or infinitely many. This is, by the way, a big hint for doing your homework and your test. I mean, if they're asking how many solutions does it have, you just whittled it down to 3 possibilities here. Don't bother thinking of 3 or 28 solutions. No, those can't be right. It's either 0, 1, or infinitely many. 0 solutions come about when, okay, so if you have a row of zeros and then something not 0, then that's a contradiction. So 0, 0, 0, 0, 0, and then something not 0 on the other side of the equals, that's a contradiction, and so there is going to be 0 solutions. That's what happens there. Whenever you have a column without a pivot, in other words, whenever you have to skip one of those attempts to get a 1 and move to the right, that means that column can be any value. That means there are infinitely many solutions. Okay. If there are no contradictory rows, and if there are no skipped columns, okay, this, by the way, when I say a skipped column, this also includes columns I didn't even get to. Like this one, this column I didn't even get to. This is also free to be any value. See, any value. So a column without a pivot, either a skip column or a column I didn't even get to, can be any value, and so that means there are infinitely many solutions. If there are no contradiction and no skip columns, not even columns that I didn't get to, then there's one solution. Okay. So basically this is the one where you're going to see ones down the diagonal, and then that's it. There's no, I reached the end of the matrix, so that's typically what means what happens. When if you have a 0 equals 0, in other words, 0 all the way across, that does not mean infinitely many solutions. Sometimes students, after a few examples, tend to think that, but actually it means nothing. It does not mean infinitely many solutions. It does not mean no solutions. It just means that row is useless and doesn't tell us anything new. The last thing that I wanted to ask is what happens if we get both a contradictory row and a skipped column. A contradiction row tells you there's no solution. A skipped column means there are infinitely many solutions. What happens if we have both? Both a row of zeros that turn into a 5 and then a column that I had to skip. The answer is there's no solution. As soon as you get a contradictory row, we know that there's no solution. All right, so that's it. I will talk to you next time. Practice a lot of these sorts of things, and we are going to see, the last bit of Gaussian elimination next time. Make our final observations about that. So, all right, take care. I'll see you next time.